In step 4, modal masses. And M1. So we take the transpose of our first mode shape. We've got our mass matrix. And our mode shape. Now I find this easier to solve by doing this bit first and then doing this bit, so I'm going to rewrite out this bit, 1.115. And this is going to give me another vector, so I'm going to write that as a vector. We've got m times by 1 plus 0 times by 1.115, so that's obviously going to be m. And here we've got 0 times by 1 plus 2m times by 1.115, so that's going to be 2.23 m. And then these two vectors can be multiplied together relatively straightforwardly, and that's going to give us a value. So we've got 1 times by m plus 1.115 times by 2.23 m. Okay, and that gives us, I'm not going to go through the process, 3.486 m. That's our first modal mass, m1. We go through the same process for m2. Mode shape transposed. Mass matrix m, 0, 0, 2m. Another mode shape. Again, I'll do this bit first. M. Point 448 square times by 2 is 0.896. And then if we go through this process again, as M2, 1.4014 m. So this is using that equation, mi x I transposed mass matrix x I. So that's step 4. Step 5. Rescale to find phi. So that equation, basically we say u, we'll do the first mode shape, 1, is going to be x1 divided by the square root of m1. So we take our x1, which is 1 and 1.115, and we divide that by the square root of m1, which we found to be 3.486 m. Okay, so you take each of these terms and you divide them by 3.4867. So you get, it's going to be quite clearly 0.536 divided by the square root of m, because obviously that we don't know what it is, and 0.598 divided by the square root of m. Now this scaling is exactly the same as this scaling, okay? If we divided this by 0.536, we get 1. If we divided this by 0.536, we get 1.115, okay? So the scaling, the ratio between those two is exactly the same, okay? We've just rescaled it to a different, instead of 1 up here, we've got this term. And so obviously what we can do is we can write this one out, write the root m outside, and then we end up with a vector 0.536 and 0.598. So that's U1. We do the same process for U2. X2 divided by the square root of M2. So that's going to be 1 minus 4.448. Square root of 1.4014m. Then if we do that, get another vector 0.845 over root m, and minus 0.379 divided by root m. So that's 1 over root m, 0.845 minus 0.379. There's our U1 and U2. Well, phi, basically, which is what we were trying to find. One over root m. Zero 0.536, 0.845, 0.598 minus 0.379. There's our modal matrix. Okay, that's our key to unlocking this process. Okay, step 6, we've got to deal with the applied forces. Okay, now if you remember, we had F1 and F2. So we'll call this P, T. That's going to be a vector. We take our modal matrix, we transpose it, and then we multiply it by our force vector. And so we've got P1 and P2. Okay, they're both functions of time. Also forget the root m term. 1 over the square root of m. We apply this matrix, 0.536. And then obviously this term is going to be minus 0.379. Transpose, those two terms swap round. 0.598 and 0.845. F1 was CT, F2 was 0. And so quite clearly what we're going to have here, we've got 0.536 over root m times by CT plus this term times by 0. Well, that's quite clearly going to be 0.536 over root m times by CT. And for P2, so we've got this term times by CT plus this term times by 0. So it's going to be 0.845 over square root of m times by CT. Step 7, our equations are modal equations. They'll always be in the form, it's undamped, qi double dot plus omega I squared qi equals pi t. So quite clearly we're going to have q1 double dot plus, or omega I squared, we found our omega terms in the previous steps. Zero 0.655 k upon m. Remember that's omega I squared times by qi, q1 in this case, equals p1, 0.536 over root m ct. And in this question, I've substituted that to be C1t, where C1 is 0.536. Whoops. C divided by root m. Just to make things clearer, I've just replaced that term with C1. Okay. Q2, same form, plus 0. Oh no, what was it? 5.536, 346, 5. K upon m. That's by Q2. And that's going to be our second term, 0.845 over root m ct. And like I said, just making a substitution to clear that up. ct, c2, 0.845. Okay. This indicates that we're dealing with a ramp function. Now the solution for this equation okay, we've solved. That's in the equation sheet. Initial rest conditions, linear increasing forcing function, x of t equals minus f upon k omega naught sine omega naught t plus ft upon k. Okay, that's right there in the solutions, straight away. We can see quite clearly that for this solution, m is 1. Well, there's no m, so we don't need to worry about that. This term is going to be our k term. Okay, so k equals 0. So for this one, okay, 0.655 k upon m. Our f is going to be C1. Okay, we know m is 1, and omega naught is going to be this term square rooted. So that's going to be, we've got that in our problem. So you can plug it into this equation to find Q1 minus C1 divided by, we've got K times omega naught. Well, that's going to be this term times by this term. So that's basically going to be this term cubed. So I call that omega 1 cubed. This is omega 1. Okay. omega 1 cubed. Sine omega 1 t plus c1 t divided by omega 1 squared. And Q2 follows a similar format. Q2 t minus c2 over omega 2 cubed sine omega 2 t plus c2 t over omega 2 squared. Okay, so we've used this solution. We know this equation has this solution. Therefore, this equation must have the same solution, okay, but in a slightly, with the terms swapped round. K we know is omega 1, okay, this term here is, K is omega 1 squared and omega 2 squared. So you've got omega times by omega, omega squared times by omega gives you omega cubed, okay. Omega 1 swaps in for omega 0 in here, and then we've got C for F, T, and then omega squared at the bottom, okay. So there's our Q1 and Q2. For I equals 1, we match this equation up with this equation here. Okay? Okay? It's quite clear from that the M is going to be 1. Okay? M is 1. M doesn't feature in this equation, so I didn't bother writing it down. Okay? F is going to be C1. Yeah? And K is going to be this term, which is omega 1 squared. Yeah? Because that's what's here, omega 1 squared. K is omega 1 squared. So if that's what I've written, I'll write it out a bit clearer. Okay? We know that F is C1. And we know that omega 0, because that features in this equation, we know that's going to equal omega 1. Okay? Is that clear? And that's because this term here, that's omega 1, okay? Sorry, omega 1 squared, yep. And so, knowing these things, we plug those things into this equation. And obviously replace Q with X, because we're solving for Q, not X this time. So Q1, T, is minus F, well that's C1, over, we've got omega 1 squared times by omega 1. It's going to be omega 1 cubed, okay? Sine of omega 0, well omega 0 is omega 1, so we replace that here, times by t, plus, we've got ft, so that's going to be c1t, over k, which or k we know is omega 1 squared. So you plug that in, okay? And exactly the same process for I equals 2, the second one, you get those two equations. Okay? Right, step 8. Convert back to displacement. Well, that we apply the substitution. Well, I shan't write this out in full because it becomes a writing competition. We've got 0.536 root m times by Q1 plus 0.845 Q2, the next 2 Q2. And that's basically using our modal equation, okay, which as we know is 1 over root m. And those, obviously, these equations up here. Okay. But I'm not going to write it out in full because it's just, just complicates matters.